Hello everyone and welcome to Network Playroom. In this video we're going to talk about the types of PGP neighbor relationships. On the right side of my screen here I have a blog post open from ipwithease.com, and this table describes the differences between iBGP and eBGP neighbor relationships, and I'll point some things out as they are relevant to our topic today, but we're not going to break down the entire table in this video. Now, before we dive into the specifics, let's first discuss PGP terminology quickly. Now, any router that runs PGP is known as a PGP speaker. The term PGP peer has a specific meaning, and it is a PGP speaker that is configured to form neighbor relationships with other PGP speakers to exchange routing information. Now, PGP peers are also known as PGP neighbors, and they can be either internal or external. We'll come back to the internal and external part momentarily. But before we do so, let's actually write down a short summary of these terms. So we had PGP speaker, which means that the router is running PGP, but it does not mean that any PGP neighbor relationships have been configured or any PGP peerings have been formed. So let's write down runs PGP. Now, PGP peer means that a PGP neighbor has been configured and a PGP session is available. Actually, I personally prefer to make a distinction between the PGP peer and PGP neighbor. I'll come back to that shortly. But let's say PGP peer and PGP neighbor has been configured. Whoops. Oh my gosh, I can't write today. Configured. Just about could fit it there. Now then finally we had PGP neighbor. And this is effectively the same as PGP peer. So these terms can be used interchangeably. And you might actually see all of these terms used interchangeably, but understand that there are those slight differences. So just be aware that the terms might not be technically perfectly accurate depending on the context. Now, how I like to differentiate these two terms if we're being really specific. So to me, personally, PGP peer means that the session has formed and the actual PGP peering is available, whereas the neighbor, a PGP neighbor, means that the session has been configured, but it's not necessarily up and running, if that makes sense. I don't know if this is the official definition, so let me know in the comments if you have different thoughts. But again, those can be used more or less interchangeably. All right, so let's move on. Now, when the PGP peers are in the same autonomous systems, it is called internal PGP or iBGP. And when the PGP peers are in different autonomous systems, it is called external PGP or eBGP. Let's write that down here as well. Now, internal PGP means neighbors are in the same AS, and the then external PGP means that the neighbors are in different AS. and we'll talk about the differences next. Now, PGP behaves differently depending on whether the neighbor is an iBGP or eBGP peer. Now, there are differences in the session establishment and route exchange mainly. Now, this video covers the session establishment part, and we'll break down the route exchange and other things in another video. But you can get some hints about that subject on the table here on the right side of the screen. Now, anyway, regarding the session establishment, eBGP imposes certain rules and restrictions which are not present in iBGP. And before we talk about the specifics of iBGP and eBGP sessions, let's actually think about what would be inside the packet headers. And this will be important when we come back to those rules and restrictions I mentioned. Now, first, let's just think about a normal TCP session. Let me draw two routers here. This one we'll call this guy R1, this one is R2. They are directly connected, and let's say, excuse me, so they are directly connected, and this is the network between them, 192.168.12.0/24. And let's say this one is .1, this one is .2. Now, if I ping from R1 to R2, what are going to be the source and destination IP addresses? Now, the destination IP address is easy. That is the IP address we want to ping. So in this case, 192.168.12.2. So let's write that down. Destination IP. 192.168.12.2. But what about the source IP address? How is the source IP address defined? Now, as you may know, by default, it is the IP address of the exit interface. So what is the exit interface in our case? It's this one, right? So the IP address, the source IP address, is going to be 192.168.12.1. Now here's an interesting question. Can the source IP address be something else? And the answer is yes. You can specify it with the source parameter in the ping command. Now you can source the ping from a specific interface, and the router will use the IP address of that interface instead of the IP address of the exit interface, which again is the default behavior. So when we do this command from R1, ping 192.168.12.2, so we can use this source parameter to specify another interface. So let's say R1 has a loopback 0 interface here with the IP address 1.1.1.1. So we can source the packet from this address. So effectively, what is going to happen, it's going to replace this address with 1.1.1.1. Okay, are you with me so far? Now, why is this concept important? Well, because PGP expects the packets to have the same IP address as is defined in the neighbor command. Otherwise, the packets will not be accepted and the PGP session will not be established. So let's say that we configure a PGP session between R1 and R2 using the directly connected interfaces. And let's say that they are both in AS65001 for now. So on R1, we would configure neighbor 192.168.12.2 and remote AS. Oh, I can't really fit it here, 65,000. And on R2, we would do a mirror configuration of that. So 192.168.12.1 remote AS 65,001. Now, as you can see here, these IP addresses configured in the neighbor command would match what would be in the packet as we just saw here. So this neighbor relationship using the directly connected interfaces would work like charm. Now you can also configure a PGP session using the loopback interfaces, but there is going to be an issue because what if we change these neighbor IP addresses? Actually, let's pretend that R2 also has a loopback interface here with 2.2.2.2. So if we were to change this, it's gonna get a little tricky here. Now what's going to happen is that the neighbor IP addresses are configured correctly, but now when the routers actually send the packets, the source IP addresses are not correct. So when R1 sends this packet to R2, then the IP address is still going to be the IP address of this exit interface right here. So what can we do about that? Now, similar to the ping command, where you can specify the source IP address, PGP has a parameter in the neighbor command that allows you to modify the source address. And this is done with the update source keyword. So we would actually add a command here. So this part would be neighbor 2.2.2.2 and then update source, loopback 0, and same on R2, neighbor, I don't know what happened there, neighbor 1.1.1.1, and then update source. My writing is so terrible today. Okay, update source, loopback 0. Okay, let me clear this out a little bit. So let me remove this here so you can see the different configuration. You would still need the remote AS specification as well, but I have just left it out to make it a little bit clearer on the screen here. But effectively, this section right here is, oh my goodness, this is for directly connected PGP peering. And this part is for using the loopback interfaces. I hope that concept is clear. In the next video, I will probably do a demo on GNS3. I should have it up and running now, so I can actually do some hands-on labs to show you this. Okay, so let's move on now. Now another key component you need to remember is the TTL value. Now briefly, the TTL stands for time to live, and it is a field in the IP header, and it's used to break possible loops. So each router decrements the value by 1, and if the value goes to 0, the router drops the packets. And this is how you prevent those loops. Now the maximum value for TTL is 255. Let's write that here. Max TTL is 255. Now the default value for eBGP is 1 and for iBGP is 255. So what does this imply? Well, that means that by default, eBGP peers can only be one hop apart, whereas iBGP does not have any restrictions other than the TTL max value. And actually, let me go back to this table because I said I would use it to point out some things, but I still haven't so far. So we're interested in this part, for example, neighborship. So as I mentioned earlier, both routers in eGP need to be in different autonomous systems. And then with internal PGP, they're going to be in the same autonomous systems. So right now we're looking at this part about the TTL. By default, eBGP peers are set with the TTL of 1, which means neighbors are assumed to be directly connected. And for iBGP, the peers are set the TTL of 255. So this is for iBGP, the max value, and default eBGP DTL, is 1. So now I'm going to discuss about a common source of confusion. And this is something I've struggled with myself when I was first learning PGP. Now, by default, eBGP neighbors have to be directly connected. So there are actually two components to this. So first is the TTL value, which we just talked about. So for eBGP, it's 1. So that already means that the routers can't be further than one hop apart, because once let's say R1 sends a packet to R2, then R2 would not forward it any further because the TTL value would go to 0 and it would drop the packet. Now second, the routers perform what is called a directly connected check, which means that the router verifies if the PGP neighbor address is directly connected from the routing table. Okay. So now let's imagine this scenario with R1 and R2, but we're going to put them in different autonomous system. So they're no longer in the same autonomous system. Let's say that this one is now in 65,001 and this one is in 65,002. Now the directly connected situation is going to work just fine. So what we had configured right here in my really messy screen right now. But what happens if you peer eBGP neighbors using loopback interfaces? Well, by default, it will not work. However, the reason why it doesn't work might not be what you think it is, and this is the part that can confuse students. So the connection is not dropped because of the TTL value. Now with the TTL of 1, the packet will still reach the neighbor router and hence the loopback interface. Now the real reason why the eBGP peering using loopback interfaces is not going to work by default is the directly connected check. Now the router will discover that the neighbor is not directly connected, so the PGP session will not form. So does that make sense? So we're looking at this scenario right here. And of course, I forgot to point out that we would need to change this AS number if they were in different autonomous systems. Okay, so back to the directly connected check. Now, how can we overcome this? Now, you can simply add the disable connected check command to allow the PGP peerings to establish in this scenario. And there are other ways to work around the default behavior, like the eBGP multi-hop command, but we will not discuss that further in this video. It's just going to complicate things. So in the loopback interface situation, you still need the update source specifications, but now one more thing you need to add is this disable connected check command. So in the case of R1, for example, it would be 2.2.2.2 remote AS. That's not going to be in the command. So disable connected checks. You would write it like this. Disable connected check. And same with R2. Neighbor 1.1.1.1 disable connected check. And apparently I still don't know how to write. Disable connected check. Okay, I don't know if this all was terribly confusing. My screen is certainly very messy here. So now, especially for eBGP, let me try to summarize what you need to remember. So by default, the TTL value is 1. So that means that they cannot be further than 1 hop apart. If you configure an eBGP peering using the directly connected interfaces, that will work because, yeah, they're 1 hop apart, so the TTL is not a problem, and they will pass the directly connected check. However, with the loopback interfaces, you need to modify the configuration. So first of all, you need to add the update source command to make sure that the packets are sourced from the right IP address. And then second, you need to disable the directly connected check to allow the PGP peerings to establish. Now with iBGP, you don't have these same issues. There's no directly connected check in iBGP, and the TTL value is 255 by default. So iBGP peers could be multiple hops apart. Okay, that's it for this video. Again, as I mentioned, I will try to demonstrate all of these concepts in a lab in the next video. Hopefully it'll make more sense. Thank you for watching, and I'll see you in the next video.